Hello students, in this lecture we will see how to design a one-way simply supported slab. Let me revise the steps involved in the design process of one-way simply supported slab. First of all, we check the aspect ratio of the slab panel. Aspect ratio is the ratio of longer span to shorter span. If it is greater than 2, we design the slab as one-way slab. Now, in step number 1, we consider the Lx, that is equal to span, and Lx is the shorter span length. So, in step number 1, we decide Lx. Then in step number 2, we determine the effective depth d, small d. It is given by the ratio span upon basic L by D ratio into modification factor. The basic L by D ratio is given as 20 for one-way slab and it is considered from deflection criteria. Here the maximum deflection allowed is considered and the basic L by D ratio is given as 20 by IS 456 2000. Then the modification factor MF, it depends upon four different parameters that we studied in the previous lecture, that is in lecture number 13. In examination, if the modification factor is not given, you can assume MF as 1.4 to 1.5. Then using this relation D equal to span upon basic L by D ratio into modification factor, find the value of small d. Then assume effective cover as 20 mm to 25 mm. Add that effective cover to this small d to get overall depth, that is capital D. Then in the third step, we calculate effective span, L effective. It is given by the relation L effective is equal to clear span plus D or center to center distance between support, whichever is less. Once we get effective span, in the next step, that is in step number 4, we calculate loading on the slab. The loading consists of dead load, live load and floor finish load. DL, that is dead load, is 25 into D, where 25 is the unit weight of RCC in kilonewton per meter cube, whereas D is the capital D is the overall depth of the slab in meter. Then live load, it depends upon the use of the slab. It is considered as 2 kilonewton per meter square for residential floor slab, 4 kilonewton per meter square for public building floor slab, and if it is a roof slab, access provided, it is 1.5 kilonewton per meter square, and if access is not provided for the roof slab, it is considered as 0.75 kilonewton per meter square. So all this load is in kilonewton per meter square. Then the floor finish load, if it is not given in the numerical, you can assume it as 0.75 to 1 kilonewton per meter square. Then add all these dead load, live load and floor finish load to get the total W UDL and then multiply it by the partial safety factor for the load 1.5. So factored UDL is equal to 1.5 into W working load. Then in step number 5, find the ultimate moment or factored moment. It is equal to WU L effective square by 8. Once you get the value of mu, equate this mu to mu max in step number 6. Mu max depends upon grade of steel. For Fe250, it is 0.149 FCK BD square. For Fe415, it is 0.138 FCK BD square. And for Fe500, mu max is 0.133 FCK BD square. Here you will consider the value of B as 1 meter, that is 1000 mm, as we are considering the 1 meter width strip of the slab. Then check that this D calculated, D required is less than D assumed in step number 2. If D required is less than D assumed, then it is okay. Otherwise, you will have to increase the assumed depth in step number 2 and revise the step from step number 3. Revise the calculation. Now, let us consider D required is less than D assumed. Then we will go towards next step, that is calculation of main steel AST, that is main steel in step number 7. That is calculated by using this formula. Here substitute the values of FCK, that is grade of concrete, FY grade of steel, MU as the moment calculated in step number 5, B 1000 mm, and D you will substitute the value of small d as we have assumed in step number 2. Calculate AST, then assume the diameter of the bar. It may be either 8 mm or 10 mm or 12 mm. Find the area of one bar and calculate the spacing. S is equal to A1. A1 is the area of one bar into 1000 divided by AST. Check that this spacing is less than 3D and spacing is also less than 300 mm. After finding main steel, the next step, that is step number 8, to find distribution steel. The amount of distribution steel depends upon whether you are using mild steel or torch steel. For mild steel, the area of distribution steel is 0.15% of A gross, whereas for torch steel, the area of distribution steel is 0.12% of A gross, where A gross is B, which is again 1000 mm, and multiplied it by capital D, that is overall depth, because we are considering the A gross area. Then assume diameter of the bar 6 mm for mild steel, and if you are using torch steel, assume 8 mm diameter bar. Find area of one bar, cross sectional area of one bar, and find spacing again by using formula A1 into 1000 divided by ASTD. Then check that this spacing is less than 5D and this spacing is also less than 450 mm. And the next step is to draw the details of the design. So this is the standard cross section, and in shorter span direction, this is AA is the cross section in shorter span, and section BB indicate the cross section in longer span direction. Show the arrangement of main steel and distribution steel. Main steel is laid along shorter span direction, whereas the distribution steel is laid along longer span direction. Bend the alternate bar of the main steel at a distance 0.1 L from face of the support. So this is the procedure of designing the one-way simply supported slab. Now let us take one example. Now in this, the given thing, I will just read the problem. Design a floor slab over a passage. Design a floor slab over a passage of size 8 meter by 2.8 meter, provided in a public building. The slab is supported by 230 mm wide beams. Consider modification factor 1.4. Use M20 and FE415. So I will write data. Design a floor slab over a passage of size 8 meter. So longer dimension is 8 meter. Shorter dimension Lx is 2.8 meter, provided in a public building. So it is given as it is a public building. This data is useful for us while deciding the live load. So public building floor slab, we consider live load as 4 kilonewton per meter square. The slab is supported by 230 mm wide beam. So width of support 230 mm. Then it is given that modification factor as 1.4, M20, that is the grade of concrete, and grade of steel is Fe415. Solution. First of all, we will check the aspect ratio. Aspect ratio is Ly by Lx. Here in this case 8 divided by 2.8. It is definitely greater than 2. So we will design it as one-way slab. Then in step number 1, we will consider the span as Lx, which is equal to 2.8 meter. In step number 2, we find the depth. Considering deflection criteria, D should be greater than or equal to span upon basic L by D ratio into modification factor. So D must be greater than or at the most equal to span is 2800 in mm, basic L by D ratio 20, and modification factor is given as 1.4. So D equal to 100 mm. Then I will assume cover, effective cover, assuming effective cover as 20 mm. Calculate D, capital D, overall depth is equal to D plus this effective cover. So 100 plus 20, that is 120 mm. So capital D assumed is 120 mm. Now in step number 3, we calculate the effective span, L effective. L effective is given as clear span plus D, or center to center distance between support, whichever is less, whichever is less. Now clear span is 2800 plus D 100, that is 2900, and now the slab is supported on 230 mm wide beams. So this is 230 mm on both the sides, the width of the support. This is given as 2800 clear span, and now the center to center distance between the support is 2800 plus 230 by 2 on one side plus 230 by 2. We are taking center to center, so 230 by 2 on both the sides. So it is 2800 plus 230 by 2 plus 230 by 2. So this is 3030 mm. Whichever is less is to be considered. So effective span, I will consider it as 2900 mm. So L effective is decided from step number 3. L effective is equal to 2900 mm. Okay. Now the step number 4, loading. Step number 4, loading on the slab. The loading will consist of dead load, live load, and floor finish load. So first of all, dead load is given as 25 into D. 25 is the unit weight of RCC fixed in kilonewton per meter cube, and is the overall depth of the slab. So 25 into D is in meter, of course. So it is 3 kilonewton per meter square. Then live load, as it is a public building floor slab, we will consider live load as 4. Then the floor finish load, as it is not given, I will assume 1. So add the total load to get W, that is 8 kilonewton per meter, as we are considering for 1 meter wide strip of the slab. Then factored load WU is equal to partial safety factor 1.5 into W, that is 1.5 into 8, that is equal to 12 kilonewton per meter. This is the factored UDL acting on the slab. Then step number 5. In step number 5, knowing the effective span and the factored UDL, we calculate mu is equal to WU L effective square by 8. WU is 12, L effective is 2.9 in meter square by 8, that is equal to 12.615. Moment is in kilonewton meter. Now, in the next step, that is in step number 6, equate this mu to mu max. Mu max depends upon grade of steel. Now here we are using Fe415, and for that mu max, for Fe415 mu max is equal to 0.138 FCK BD square. Now I will calculate the required D to resist this bending moment by equating these two. So mu is 12.615, mu is 12.615 into 10 raised to 6 is equal to 0.138 FCK BD square. Here FCK is 20 because the grade of concrete is 20. B 1000 mm. Remember, slab is a beam of width 1 meter, and this is D required. So simplifying this, find D required is equal to 67.60 mm. This D required is to resist the given bending moment, that is 12.615 kilonewton meter. This D required is less than D assumed. D required is 67.6 mm, which is less than D assumed is 100 mm. So it is safe. Okay. Now we can proceed to find steel, area of steel. So in step number 7, main steel, AST. AST is given by the formula 0.5 FCK upon Fy into bracket divided by FCK BD square into D into D. Here FCK is 20, Fy is 415, then Mu is 12.615 into 10 raised to 6. Remember, convert it to Newton mm. B is 1000 and small d, that is the depth that we are going to provide considering the deflection criteria in step number 2, that we assume that is small d is 100 mm. So substitute these values and find AST. You will get the AST as 385.5 mm square. Now after finding AST, let us assume diameter of the bar. Assume diameter of bar as 10 mm. A1 is the area of one bar, that is pi by 4 into 10 square, that is 78.5. 78.5 mm square. Then find the spacing of this bar is equal to A1 upon the AST into 1000. A1 is 78.5 divided by AST 385.5 into 1000. So here after calculation I will get the spacing as 203.6 mm. Always round it to lower side 200 mm. Center to center. This is the spacing. Now check that this spacing is less than 3D, where D is the effective depth. So 3 into 100, that is 300 mm. And spacing should also not be greater than 300 mm. So yes, we are providing spacing as 200 mm, it is less than 3D as well as 300 mm. Now in the next step, that is step number 8, we find the distribution step, that is say ASTD. We consider ASTD as 0.15% for mild steel of A gross, of course, of A gross. Let us consider assume for distribution mild steel is used, that is 6 mm diameter bar. Now ASTD, you can assume torch steel also, but in that case you will have to take ASTD as 0.12% of A gross. So 0.15% of A gross B into capital D. So 0.15 divided by 100 to 1000 into 120. Remember here we consider overall depth because we are considering the gross area. So this is equal to 180 mm square So we will find spacing of 6 mm diameter bar. Area of one bar, that is pi by 4 6 square, is say 28 mm square. Then spacing is equal to A1 upon ASTD into 1000, that is 28 divided by 180 into 1000. So here the spacing is 155 mm. Always round it to lower side, say 150 mm. Check that this spacing, check, this spacing is not greater than, or it should be less than 5D, and spacing should not be greater than 450 mm. So as we are providing 150 mm spacing, it is less than 5D, where D is 100 mm, and it is also less than 450 mm. So okay. Now I will write the conclusion. Overall depth of the slab, that is capital D 120 mm. Effective cover 20 mm. Then steel along shorter span, that is main steel 10 mm diameter torque at 200 mm center to center, and steel along longer span, that is distribution steel, is equal to 6 mm mild steel. See the sign convention, mild steel at 150 mm center to center. Then the last job is to draw the sketch. Step number 9, detailing. In the previous lecture, I explained the detailing. Here, I will again explain how the arrangement of the bar is to be shown. See, this is our shorter span, whereas this is the longer span, Ly. This is Lx. First, you will lay this main steel bar, bend it at a distance 0.1 L. Here L is 2.8, so into zero point 0.1. So here you can bend it at 0.8 meter. And take this bar up to the end. Rest it on this support beam. Then the alternate bar is bent on other side. See, lay this bar like this, take it up. At general, the angle is 45 degree. It is bent at an angle of 45 degree. So this is the main steel. In our problem, this main steel show on the drawing the spacing main steel 10 mm tor at 200 mm center to center like this. Bend this bar from the face of support at a distance 0.28 meter. So likewise you will lay the main steel bar along shorter span direction, and then the distribution steel is given as 6 mm diameter at 150 mm center to center. So this is the distribution steel, straight bars. These are the distribution steel. And so distribution steel I am drawing, showing with this green ink. Along this longer span you will show the distribution steel. So these bars are 6 mm mild steel at 150 mm center to center. You can draw the cross section along A, that is along shorter span. This is along shorter span, cross section along shorter span, whereas this is cross section along longer span. Here you can see that is along shorter span cross section. You will see the at this bottom their main steel is there, and on above the main steel the bars are distribution steel. So this is distribution steel. Whereas these dots you can see in the cross section below this distribution steel is the main steel. Similarly, here you will see that along shorter span at the bottom there is main steel, whereas these dots indicate distribution steel. And remember, where the bars are bent and taken up, you will provide minimum 2 bars at the top as distribution steel. Minimum 2 bars. So this completes the design and drawing of one-way simply supported slab. Thank you.